The recent Viking Flame test campaign, conducted jointly by Sweden and the United Kingdom, marks one of the most strategically relevant steps in NATO's ongoing effort to harden its fighter aviation against increasingly sophisticated multi-domain threats. Running from November 10 to 14, 2025, at the Donna Nook Air Weapons Range in Lincolnshire, the trials brought together Swedish and British defence authorities, operational units, and scientific research institutions. Their goal was clear: to evaluate next-generation aircraft self-protection systems under realistic, replicable, and highly contested conditions. For NATO, which faces an accelerating evolution in radar-guided missiles, long-range air defenses, and dense electronic warfare environments, the data and methodologies generated during Viking Flame represent a critical foundation for the survivability of future air operations. The project was executed under the umbrella of the UK-led Project Easyrider, an initiative that remains largely classified but is widely recognized as one of the most agile development frameworks within NATO's air domain. Unlike traditional defense acquisition processes, which often span years or even decades, Easyrider focuses on compressing the timeline from early prototyping to frontline integration. It achieves this by blending modular testbeds, rapid system swapping, real-time analysis, and multinational participation. Viking Flame's structure reflected this philosophy: a compact 5-day testing window, multiple flight sorties, and iterative adaptations based on live results. Rather than evaluating single technologies in isolation, the campaign examined how integrated self-protection systems, expendables, jamming suites, countermeasure techniques, sensor fusion, and digital electronic warfare perform holistically against air defense architectures modeled on near-peer adversaries. A core element of the trial was the use of two Saab JAS 39 Gripen fighter jets from Sweden's FMV Test and Evaluation Unit, operating out of RAF Koningsby. The choice of platform was intentional. The Gripen is known for its modular design and rapid integration capabilities, making it ideal for a test environment where electronic warfare packages, new expendables, and experimental software can be swapped and assessed in a matter of hours rather than days. During 6 instrumented flights, conducted despite challenging weather, the Gripens were exposed to calibrated radar threats, infrared-guided missile simulations, and complex electronic attack scenarios. These flights provided high-fidelity datasets capturing how emerging self-protection technologies perform when layered together and applied dynamically in operationally relevant conditions. The value of these trials extends well beyond the Gripen itself. Because the data focuses on system behavior and threat response rather than platform-specific characteristics, it becomes transferable across multiple NATO aircraft, including the Eurofighter Typhoon, F-16, F-35, and future 6th-generation airframes. In practice, this means that survivability solutions validated during Viking Flame can inform upgrades across both legacy fleets and upcoming fighter programs, enhancing the baseline protection of NATO aviation as a whole. This interoperability focus is one of the pillars of Project Easyrider, to create a testing ecosystem where lessons learned in one aircraft environment can feed directly into multinational force modernization. The realism of the Viking Flame campaign was made possible by its sophisticated test architecture. Ground-based threat emulators were paired with airborne assets, creating a multi-layered environment that mimicked near-peer integrated air defense networks. As modern conflict has demonstrated, from Eastern Europe to the Middle East, fighter jets no longer contend with isolated missile systems but with tightly coordinated, networked arrays of sensors and interceptors. The ability to evaluate countermeasures against such systems in a controlled setting gives NATO a rare opportunity to experiment with new tactics, refine electronic warfare timing, and assess how sensor fusion algorithms prioritize threats under pressure. Collaboration was a defining feature of Viking Flame. The planning and execution were led jointly by the Royal Air Force's Air and Space Warfare Centre and the UK Defence Science and Technology Laboratory, with substantial support from Sweden's Defence Materiel Administration, the Swedish Defence Research Institute, and the Swedish Air Force. This integration of operational end users, scientific experts, and national defense bodies represents the future direction of military capability development. As modern threats evolve faster than procurement cycles, the ability to gather data, process it collaboratively, and translate findings into deployable upgrades becomes a strategic necessity. The campaign demonstrated how Sweden and the UK, countries with different air doctrines but shared security concerns, can synchronize testing, analysis, and application in real time. Strategically, Viking Flame arrives at a pivotal moment. NATO is confronted with the resurgence of peer-level competition, marked by expanded A2/AD zones, increasingly capable surface-to-air missile systems, and adversaries investing heavily in electronic warfare. In this context, fighter survivability is no longer a secondary consideration but a prerequisite for maintaining air superiority. The campaign's outcomes reinforced the importance of survivability as a system-of-systems challenge. No single countermeasure is sufficient on its own, but integrated defense suites, coordinated through intelligent software, can dramatically increase pilot survivability and mission success rates. Another key implication lies in the Gripen's export-ready nature. By validating emerging defensive technologies on a widely operated, NATO-compatible fighter, Sweden and the UK create pathways for partner nations to adopt similar survivability enhancements without starting from scratch. This accelerates collective modernization and ensures that Allied air forces maintain comparable protection levels when operating together. Such harmonization is vital for joint operations, where unequal survivability capabilities can create operational gaps and undermine mission cohesion. Ultimately, Viking Flame underscores why multinational testing campaigns are becoming essential rather than optional. As threat systems continue to diversify, from long-range SAM complexes to advanced infrared seekers, the only effective response is shared experimentation, pooled intelligence, and cross-platform data exchange. The results from this campaign will feed into ongoing modernization efforts, influence design decisions for next-generation aircraft, and help shape the evolution of NATO's air defense doctrine. In sum, the Viking Flame trials represent more than a technical evaluation. They demonstrate a shift in how NATO prepares for future conflict. Through agility, collaboration, and rapid integration, Sweden and the UK have shown what a modern, forward-looking survivability development model looks like. For Allied air forces, the data captured over Lincolnshire is not just a snapshot of current capability, it is a blueprint for staying ahead of evolving threats in an increasingly contested battle space.